Let's look at the distinction between what are called objects versus systems. And I've given a simple problem here. We've got no friction. We have block A and block B. The masses of each block are given here. And we see that we have 40 newtons pushing to the right on block A right there. And at this point, with the analysis you've been able to do in forces, you should be able to take it from here if you're strong in the process of using Newton's second law. So I'd like you to pause the video now and just do the process. I'm not even going to tell you what to solve for here. I think it's a good exercise to see if you can just figure out where to go from here and what you could solve for and what you would do if you were analyzing this scenario. And then we'll take a look and see what types of things you can do with this information that's been given, and that will illuminate the difference between what's called an object and then a system. So pause the video and use that process that we've learned with Newton's second law to see how much physics you can do. Go ahead. So the first step is to make a coordinate system. So to the right is positive, up is positive. A simple way to do that is over here. And then the next question becomes, what is the object under analysis? And so maybe you chose object A. You draw a dotted line around object A and you ask, what are all the forces, contact and non-contact? Well, we see a push over here. We'll just assume it's contact. So 40 newtons to the right. Then there's a force from B pushing back on A to the left because of this contact right here. Got contact with the floor, that's pushing up, and then of course gravity is a non-contact force pushing down. So that's 4 individual forces that are being exerted on object A. We could do the same thing with object B, draw a box around B, and we'd see that there's a contact force to the right coming from object A pushing on object B to the right. Importantly, this 40 Newton force over here is absolutely not pushing on B at all. It's object A right here with that contact that's pushing to the right on object B. And then we have gravity pulling down. And of course, we have a normal force coming from the floor here pushing up also on B. So 3 forces on B. But interestingly, we don't know anything about this interaction quite yet between A and B. So if you did this analysis by kind of putting 2 dotted lines around each object separately like that, you would get stuck and you really wouldn't have anywhere else to go in the problem. So the way to get out of this is to invent this new method of analysis where instead of focusing on the individual objects, we look at the whole thing as what's called a system. And there's a little bit of an art to this. You have to kind of figure out what are independent objects that can kind of move around and what do you want to call like an entire system. But you really have freedom in doing that, which is nice. But I think the most logical thing in this case would be just to draw our dotted line around. Let's do that here. This entire, both of the blocks, I should say. And that we will call the system. And what is inside of the system is 2 blocks. Inside the system are 2 blocks, are blocks A and B. All right. Cool. Now that we've done that, you can think of blocks A and B as one thing. In fact, if it helps you, you can kind of like do something like that almost. And the reason you can do that is because you know that these blocks are going to move together, to the right. They're not going to be separating, and they're not going to have different acceleration values. Okay, so now what we would do is just look at that whole system and think about, is there anything we know about it, right? We put a dotted line around it. I'll just do this in a different color. Putting a dotted line around now our entire system made up of 2 objects, and ask the same question. This effectively becomes like the system under analysis, where it's like one massive object or something like that. So what forces are exerted on the system? Well, we've got a 40 Newton force over here to the right, and then we have a force from the floor pushing up, and then a gravitational force pulling down. All right, so what's the next thing to do? Well, I always recommend you just write down the second law, because it tells you what to do. And we'll do this in the horizontal direction. But specifically, the subscripting is very important. We're going to say let's sum of all the forces in the x direction on the system. And that's going to equal the mass of what? Well, the mass of the system multiplied by the acceleration of the system. So we're being very specific with our subscripting here. Another way you could write this, and I'll just write this over here on the left-hand side, is you could come along and say that the acceleration is equal to the net force divided by the mass. That's also Newton's second law, same thing, right? It's the conceptual way to write it, which in fact I tend to like better because it shows you cause and effect. Net forces cause accelerations, and those accelerations are inversely proportional to the mass. But in this context, for this problem, we would also want to be very specific and say that it's the acceleration of the system would be equal to the net force exerted on the system divided by the mass of the system. So pretty much exactly the same formula. Over here, it's just written out in the component form and in a more procedural way of how you'd go about using it. So let's do that more procedural method. Let's add all the forces up. So what do we have? Well, we've got the 40 Newton force on the system right here. And I don't have any other way of saying, hey, it's a person, it's a rocket, who knows what it is. It's just 40 newtons. So I just left it as that. So we'll write that in here. So there's that 40 Newton force on system. And then is there anything else pushing to the right? Well, inspect the problem. Let's take a look. There's no friction. And here's our border for our object. I don't see anything touching the object. Sorry, I don't see anything touching the system here else other than this 40 Newton force. And there's no non-contact interactions horizontally here at all. So we're done actually horizontally. That's the only force, that 40 Newton force. And that must equal the mass of the system times the acceleration of the system. Great. Now we plug in what we know and we can solve for our acceleration of our system. So we'd get the 40 Newton force divided by the mass. And so what is the mass of the system? Well, it's 4 kilograms. Hopefully that's obvious to you. And now when we work this out, we get 10 meters per second squared. Positive. Doesn't have anything to do with gravity. It just worked out that it's 10 based on the numbers I chose. And we would now see both block A and B accelerate with an acceleration of positive 10 meters per second squared. And if this system began at rest, well, then you would start to see it move to the right, and it would be speeding up at that rate. So notice that what we've done here is we switched into the system view, and we were able to extract information that we would not have been able to get just focusing on the individual objects. Now that we have that piece of information, namely the acceleration of this whole system, let's switch back into the individual object viewpoint and finish the problem. So what I'd like you to do now, pause the video and determine all forces, both magnitude and direction, that is being exerted on each object, or perhaps check your work if you were able to do all of this on your own from the very start of the video, which is pretty good if you did all of that yourself. But go ahead, pause the video, and in doing so, you'll draw 2 free body diagrams where you'll very clearly label all of the forces and both of their magnitudes and directions. Final point before you work, make sure that you scale your free body diagram correctly. So when you draw your force vectors, if you draw a vector that's twice as long as another one, you're communicating that that force is twice as large as the other one. So be very careful with how long you draw the arrows relative to other arrows when you draw your force vectors. All right, so go ahead, pause the video, and see if you can work out the rest of the problem. All right, so we have Newton's second law, and we can see that we add up all the forces on A in the horizontal direction. That's equal to the mass of A times the acceleration of A in the horizontal direction. The subscripting looks a little intense there, but we want to be pretty formal in the beginning just to make sure that we have it written down correctly. Then we can see down here when we plug in the forces, the 2 horizontal forces, the 40 Newton push to the right and then B back on A, which is to the left, the summation of those 2 forces is going to equal the mass of A times the acceleration of A in the horizontal direction. Now, we plug in our numbers, and we know the push to the right, 40 newtons, but we don't know the strength of that push to the left from B on A. However, in the system viewpoint, we were able to solve for the acceleration that both of the blocks have. So we can now use that, and that helps us generate new information, specifically the force that B pushes back on A. And if you just kind of work out the math here, it's pretty easy to show that the force of B on A is negative 10 newtons, and that negative sign, of course, means that it's pushing to the left. So I have the free body diagram drawn out for A. I tried to get my scaling correct. Gravity's pulling down with 30 newtons, normal's pushing up. Really nothing exciting in the vertical direction to analyze, just simple balanced forces. But then we do have 40 to the right and then 10 to the left, creating 30 newtons of net force horizontally on object A, which is causing that 10 meters per second squared acceleration because we have a mass of 3 kilograms. Go ahead and pause the video now and just finish up the diagram for B's free body diagram and see if you get something very important correct here. Pause the video and do B's free body diagram if you haven't done so. Now, importantly, A and B are interacting. And what that really means is that they're each able to change the velocity of the other object. And they do that through forces. Forces are what happen when two objects interact. And there's either a contact interaction where two things are physically touching, or there's a non-contact interaction such as gravitation, electric, or magnetic phenomenon. So we can see if we zoom in right here, because of that contact, A and B are pushing on each other. And we know, or I hope you know, through what's called Newton's third law, that when object A applies a force on object B will apply a force back on object A that is equal in magnitude but opposite in direction. And that's totally happening here. So if we were to write that out in a formula using our subscripting, we'd have the force of A on B is equal to minus the force of B on A to get the directions right. And so, therefore, we had previously deduced that B pushes on A with negative 10 newtons, and therefore there must be a force of A on B. Oops, A on B. That is positive 10 newtons, pushing to the right. And then I've indicated that over here with the free body diagram. Try to get my scaling right compared to this other diagram, which looks nice. And there we have it, a fully completed problem here. Both blocks would accelerate to the right with identical accelerations. Block A would have a net force of it of 30 newtons, 40 minus 10. Block B would have a net force of it of only 10 newtons. And that's interesting. Let's revisit the second law before we end this video. Think about this for a second. There's a lot of great information. I'll write this out. I'm running out of space, but I'll just write it right here. Think about this, that the acceleration of B is equal to the net force on B divided by the mass of B. Sorry, it's getting a little messy here. Let me draw like a line right here just to kind of get this out of the way. All right, cool. That's just good old Newton's second law. Well, we know the net force on B. And of course, this is in the horizontal direction, by the way. This is the net force on B in the horizontal direction, the acceleration of B in the horizontal direction. And we plug it in, so we get 10 newtons of net force horizontally. And then we get the mass of B, which is 1 kilogram. And look at that. If you divide 10 by 1, of course, you get 10 meters per second squared here for our acceleration. So it's a good check to make sure that we did things correctly. We're producing the same value for the acceleration in multiple ways. One way by looking at the system view, and the other way now looking at the object view for both A and B. Now to wrap this video up, you can see that there's a benefit to looking at things in the system view versus the object view. Importantly, sometimes you just don't have enough information to solve for everything if you just look at the individual objects, and you need to go into that system view. And I think I said a couple times earlier that we had to go into the system view to get the acceleration. Actually, in this problem, you can solve for everything in the object view alone without going into the system view. It's just a little bit more complicated to do that. So try that too. That's actually a good process. I misspoke earlier briefly when I said you could not get the acceleration if you just looked at the objects. You certainly can, but you need to look at both A and B, use Newton's second law, and try that. It's a good exercise to do to see if you can totally do this problem without the system view. However, you can see that it's very easy to get the acceleration in this problem by switching to that system view. And every once in a while, it turns out that in a problem, you're just not able to get the information you need unless you do switch into the system view. It just depends on what information that you have in the particular problem. All right, so with that, I hope you enjoyed this video and you learned a little bit more about how to kind of go back and forth between objects and systems and why that's important. All right, take care, and we'll see you in the next video.